transparent the light to the solar panel and can combine with the RF energy and solar and harvester based output power, harvested power. And there's a different type of the transparent antenna available in the market. So there's some transparent antennas, I think around 90, 95, 97% transparent. So you cannot see these type of antenna totally transparent. So these type of antenna you can put in your glass or car, your car or your building glass window. You can put anywhere. So you cannot see this type of the transparent antenna, and you can harvest the energy. Or this type of antenna you can put on the solar panel. So you have the hybrid type of the energy harvester. So in the night time, you can still continue harvesting the RF power, because our RF power you available in the 24 hour. Only sun is the depend on the weather conditions. So there's no sun, so still you can continue the harvesting the RF energy. So the hybrid type of the harvester maybe can work for the communication of sensor. And there I was discussing the grid type of antenna. So grid type antenna is very simple. You just have the around wavelength of the width, length, and the half wavelength of the width. So the beauty of this type of antenna, if you have the multiple feed, so you can generate the beam in the different direction. Like this antenna have the 2 feed, so you have the two beam in different direction. So you can receive the energy from the 2 different direction, and you can combine, and you can have the combine and then have the very large power density, receive power in the large area. So if you have the multiple feed or if you have the large array, and you can use this grid array antenna as a transparent also. So you can put in the solar panel, or you have the hybrid type of the energy. So this kind of the structure can generate the beam in different direction without any phase shifter or any IC. So this can be the still passive to beam in the different direction. So the one of the I think paper from US used the Nature. They published the Nature. So they proposed the Rotman lens. You know, the Rotman lens have the beauty also. If you are feeding the antenna structure, this is the Rotman lens, and this is the feeding. If you are feeding in the different places of this Rotman lens, you can get the phase difference between the 2 feed. So based on this delay, you can generate the beam in the different direction. Like they use the 8 antenna, 8 or 6. I think they use 8 antenna to generate the 8 beam in the different direction, connecting with this from this connector. So you can receive the energy from the different direction. So you can cover the large area, and because this Rotman lens beam is very directive. So they propose for the millimeter wave applications. They call like a power grid. You can generate the power grid based on the energy harvesting at the Ka band for the 5G millimeter wave. So the 5G millimeter wave going to be, I think, in future very hot. So there's a lot of base station very close to cover the area. So you can have some energy of this band. And other very interesting antenna design, I think this is we call the leaky wave antenna. So leaky wave antenna have the beauty also. At the different frequency, you can generate the beam in the different direction. So at the 3 different frequency, we have the beam in the 3 different directions without any phase shifter or anything. So this is the quality of the leaky wave antenna, beam changing with the frequency. So we know the which beam at what frequency in which direction. So based on that, we can design the sensors or load in different direction which can cover only one antenna uh, to charge up the sensor in different direction. So they have studied if you are designing the low frequency and high frequency, there's some theoretical, I think they have comparison. They mention the millimeter wave area, and the size of the antenna can be the larger, they have the high gain, and can improve the uh, efficiency, very high efficiency, improve the wireless power transfer efficiency very high. So the liquid wave antenna quality is very good. If you have the if you can calculate the beam direction with frequency, we have the angle with frequency, then you can put the sensor based on the frequency and the distance. Then you can transfer the power to the different location to charge up the sensor or any devices in the different locations. So this is very good antenna. Maybe now not much famous, but in future maybe this can be used, because if you do this frequency changing with the beam changing with frequency, so you can get the location of the beam at what frequency. So you can use this antenna for different, only single antenna in different sensors, posted different sensors. So we have also did some study to design the metamaterial based compact dual band retina. You can see in this figure, the antenna part is this part only. This is the dual band antenna, and then we have the uh, impedance matching with the retina. This is the total retina antenna with the rectifier. So this is very small. So we can put this one for the small sensors, for which can be receive the energy from two band, Wi-Fi band and WiMAX band, 2.5 and 3.5. So this is the antenna. You can see this slot antenna back of this, and we put the metamaterial antenna as the radiator. The slot can radiate both directions. So this is the two band, 2.5 and 3.6, 2.5 and 3.5. You can see here, we can get the very good efficiency between the measurement and the simulation, around the 60% efficiency of this metamaterial based retina, dual band antenna, retina. This is very interesting design for the compact sensor. So you can put this harvester with the compact sensing. The other very interesting, I think, some papers from the IEEE proceedings. Very interesting, very broadband antenna. They have designed the antenna for like the spiral type antenna. And because spiral, if you have the different direction, spiral antenna or feeding different directions, you can generate the opposite polarization also. So this is the dual circular polarized antenna, and they have the RF combining, because of each 2x2 array antenna, they have the connected rectifier and then our RF combining here, DC combining here. First RF combining and then DC combining. So like this, you can get the more power. So if you have this combination, RF combining and DC combining, if you have the very large array antenna. So this type of antenna can be used as the wearable antenna, or you can charge up your some implantable devices, or the wearable, or you have the watch, and you have some sensor, body area sensor or something. You can charge up of this antenna. So there's some papers, they use the wearable harvester for different, the hybrid type of the technology. They use some heat or this. They have also generate the energy and then combine. So they have compare here. If you have the spiral array antenna, so you have the very wide range of the DC power. And if you have the dipole based array, you have very narrow band. And grid type also have the very large band. This is just comparison. So now I will discuss some reconfigurable antenna. So you know the reconfigurable antenna, we have the 4 type of the reconfigurable antenna, like the frequency. or bandwidth, we can change the reconfigurable the frequency. We change the frequency, different frequency by changing the some using the tunable devices or tunable material or other thing. And there the other is the polarization. Reconfigurable, we can change the polarization like left to right, left to circular polarization, right hand circular polarization, or linear polarized, vertical and horizontal, or dual polarized. Another is the pattern. Pattern is very important. Pattern is we can change the beam in the different direction. So if you have the beam in this direction, so by using the some delay line or some tunable material or IC or phase shifter, we can change the beam in different direction. Another is the hybrid type of the antenna. We can have the like either frequency pattern or pattern polarization or frequency polarization. We call the hybrid type of the antenna, reconfigurable antenna. So one antenna can have the frequency change and polarization change or pattern change, beam forming, beam spreading antenna, like that. So in future also this type of the antenna is very useful for communications. So there are the different method of the designing the reconfigurable antenna. There's some like we call the tunable material like graphene, liquid crystal, vanadium oxide, VO2, phase change material. So these kind of material can be used for the reconfigurable. Either if you are using the liquid crystal as the antenna substrate or cavity, you can fill the cavity of the antenna. You can bias the this liquid crystal. You can change the permittivity of the liquid crystal. So if you change the liquid crystal permittivity to antenna, you can see change. So you can design the reconfigurable antenna using this tunable. We call the tunable materials. Graphene also tunable material. And there's a vector diode and the pin diode also can be used. And phase shifter beam forming IC. I think this is a very expensive method, but this method is very low cost. The pin diode also cannot be used very high frequency. Low frequency, okay. So if you go the terahertz or very high frequency millimeter wave, so you have to use the graphene or this liquid crystal based materials. And there are some meta surface based also, ferrite based also very low frequency you can use. And semiconductor is also can use for the reconfigurable antenna design, MEMS and mechanical. So the main challenge of the reconfigurable antenna, if you're designing the tunable material, the fabrication also very challenging. How you can control these materials or integration, and if you are going to the phase shifter or semiconductor, you have to think the power consumption. There's some non-linearity if you are using the active devices, and the measurements such the setup also very challenging. How you can have the biasing and everything. And material characterization also if you are using the tunable material. So the reconfigurable antenna technology, either electrically or mechanically, you can change the structure of the antenna. You can change the beam or can change the frequency. Other is the optical and material I discussed here. So nowadays I think the most of the research going on the liquid crystal based antenna, tunable antenna, reconfigurable antenna. And this liquid crystal is very low cost, so you can design very low cost reconfigurable antenna. So the most important reconfigurable is the pattern reconfigurable antenna for future the 5G 6G applications. You need beam forming antenna, multi-beam antenna. So how you can design this pattern reconfigurable antenna? The cost is very important. So generally, they use the conventional method is use the phase array antenna, like we have the phase shifter or IC switching network. You can change the beam in different direction. Other is the mechanical, very simple. You can mechanically change. The other is unconventional. The research going on this direction. How we can reduce the cost using the tunable material or this vector diode or this reconfigurable. Reconfigurable intelligent surface, meta surface or meta material surface. So this is very interesting area. So the material based is the low power consumption can be used the millimeter wave terahertz based band, and we have the electrically, optically, or thermal. You can change the property of the materials. You can change the beam frequency or multi-beam antenna. You can generate very easily. This is the low cost. The other one is the spin diode. I think you cannot use the very high frequency up to gigahertz. Okay. And some papers in the literature, they use the reconfigurable antenna for energy harvesting. For my understanding, for if you want to design the real energy harvesting, so no need any external power. So most of the antenna, reconfigurable antenna, they have the diode or switch, so which require the biasing. We need the power. So for wireless power transfer, okay, but I don't think for RF energy harvesting is a good idea to use the reconfigurable antenna. So this structure, they use the reconfigurable frequency reconfigurable antenna. So one antenna which connecting with the small part of this and with the diode or which, using a switch. So if you are connecting this part, you can change the frequency. If you are off, you have the different frequency. This is very obvious because the patch area is changed, the frequency is changed. So this is the just they have done the different band. So this the on and off. If the switch on, the frequency is the lower, around 4 point something, 4.8 measurement. If the switch is off, the frequency is higher because of this unconnected. The area is smaller, the frequency is higher. This is a very standard way. So they designed the rectifier, and then they have compared both band simulation and the measurement. You can see here the measured at the 4.9 and the 5.9 frequency measurement. But still, I think they achieve very good efficiency, around 60% efficiency in the both band. This is a very good. And other is they use the polarization reconfigurable antenna. So this antenna, if on and off, you can change the right hand to left hand. Oh, not right. The linear polarized to circular polarized. So if the off condition is the linear polarized because the axial ratio is very high. If the on, then the axial ratio is less than 3. So it means this antenna can work as the linear polarized and circular polarized. If they put this antenna, Y-shaped antenna on top of the meta surface, they can design the wideband antenna, circular polarized antenna. You can see here, the antenna is very wideband. So this is not really polarization reconfigurable antenna because if they put on the meta surface, they have not studied the on and off. Only just without meta surface, they study the on and off. But still, the axial ratio is the 7 dB. Still have some ellipticity of the polarization. It's not real linear polarized or not real circular polarized. And just I think this year we have accepted one paper in AWPL. We have designed the meta surface based reconfigurable polarization reconfigurable antenna. So this meta surface arranged in the different direction, and we connected the one diode with the below of the layer, and using this is the one layer only, two layer structure, ground plane, and this structure is the ground plane and this is the meta surface. By on and off, we can change the polarization, pin on and off, linear to circular polarization. Is very clear. You can see here. So the axial ratio for linear polarized antennas should be around around 40, more than 40. So this is just this year we have designed and a very interesting antenna. And other is the pattern reconfigurable antenna used for energy harvesting. So this is a good idea. So they have designed the 8 dipole and put the different direction to cover the whole, can cover the whole 360 degree, can receive the energy from all directions. So this antenna can be reconfigurable based on the switching in different directions. So idea is here. So if the source in the different direction, you can switch the beam in different direction and can receive the energy from all directions by switching the beam. And I just talk about you the grid array antenna. The quality of the grid array antenna can have the beam in the different direction, and the structure is very simple. This is the one layer structure, and this is the grid array antenna. This is the feeding. If you are feeding the multiple feeder, we use the 9 feeder, so we can have the beam 9 beam in different directions without any IC or any phase shifter. So the innovation, beam steering innovation, the innovation in the beam steering occurring directly at the antenna level, not any and not any the IC and phase shifter. So based on the location of the feed, we can have the phase delay compared to the center, so we can have the beam in the different direction. So this is a very interesting design, very simple design to get the multiple beam in different direction, can receive the energy from the different direction, and then you can combine or DC combiner or RF combiner. So we have also designed at 93 gigahertz, and we have got the patent of this energy because this is very interesting idea, and we have created the circular polarization of using this antenna by putting the circular polarizer top of the grid array antenna. So we can have the 3 feed, 3 beam. One is the center beam, another is in this direction. So we can have the energy from the 3 directions. So these are the some the published circular polarized based RF energy harvester. You can see that this is very high gain meta surface based antenna for energy harvesting. And this is a very wide band antenna. You know the slot antenna generally very wide, and they make the array antenna of this one to enhance the gain of the antenna to receive the more power. And there is some a compact and the wideband circular polarized antenna at the X band for energy harvesting they use. And we have designed some antenna. You can see here. I will present in the detail later on. So now I will discuss the circular polarized antenna design for energy harvesting. So circular polarization to generate in the antenna, you have to think how we can generate the 2 mode with 90 degrees phase difference. So here the 2 mode, you can see the horizontal and vertical with 90 degrees phase difference. So the circular polarization you can generate in the from the antenna receiving neutron. So the other in circular polarization we have the right hand and left hand based on the leading or lag of these 2 modes. So the designing of circular polarized antenna typically there's the 3 types of the feeding configuration commonly used for antenna designing, circular polarized antenna designing. There's a single feed. Generally, we can generate the 2 mode, 2 orthogonal mode using the either the some asymmetry or using the nearly square patch. So if you have the nearly square patch, slightly width or length is slightly larger, and you are feeding on the diagonal direction. So you can generate the 2 mode and with 90-degree phase difference. So you can generate the circular polarization. But the problem for single feed is the very narrow band. Another way you can have the square patch, you cut the corner and feeding in orthogonal direction, you can generate the 2 mode, one here, one here. The resonance frequency of the 1 mode slightly difference because the length is changing. I will show you how to change. The other is the dual feed. So dual feed is very simple to design. You have the square patch, you are feeding 2 mode, with 90-degree phase difference. Very easy to get the circular polarization, or you have the filter, you can add the 90-degree phase difference here. You can generate the two mode, that we have the 2 feet where you can generate the circular polarization very easily. The other is the sequentially rotate. Also, we can design very wideband and circular polarized antenna using the sequentially rotate or dual feed. But the sequentially rotate and dual feed, you need to extra space of the structure. You need to design this 90-degree phase difference and the filter or the hybrid coupler. And the other method is the sequentially rotate. So you need more than one antenna, or if you have the two antenna, you just have the 0 and 90-degree phase difference, like 0 and 90-degree, rotate the antenna 90-degree, and you connect, combine, and you can get the circular polarization. Even you have the linear polarized antenna, you can still get the circular polarization. So if you have the 4 antenna, you have the like combination 0, 90, 180, and 270 combined. If you have the linear polarized antenna, you are combining 0, 90, 180, and 270. Still, you can get the circular polarized antenna. So these two is you can design the very wideband, very simple way. But the main challenge is how we can design the wideband antenna using the single feed. Generally, we put the rectifier in the single feed. So if you have the wideband circular polarized antenna, you just connect the one rectifier, you can get use for energy harvesting. So other, I think not commonly used, but there are the different two more different way to design the circular polarization. So you have the 3 feed or 4 feed base sequentially phase circular polarized antenna. So if you have the 3 feet, so you have to have the like 0 degree, 120, and 240. You have the consistent phase difference between the port. So you can generate the circular polarization. Either you have the circular patch or you have the square patch. So you can generate the other is the 4 feet. So if you have the square patch and the 4 direction for orthogonal direction or any diagonal direction, you can generate the circular polarization very easily. For some very precise circular polarization, very perfect circular polarization, some application use this kind of topology like GPS or GNSS. They need very good circular polarized antenna, and beam is symmetric. So these type of antenna have the very good circular polarization. So you can see here, this is the 0 degree and this is the 180 degree. This is the 0 degree and this is the 90 degree. And this is 180 degree and this 270 degree. 90 plus 180 is 270 degree. So you have to, for this type of designing the circular polarized antenna is very expensive, because you have to have the 190 degree hybrid coupler to 180 degree hybrid coupler. So this overall cost is increasing. And same is if you have the circular patch, you can connect the 4 feed with the different phase shifter like 0, 90, 0, 90, 180, and 270. So you can generate the circular polarization very easily. But the main challenge, again, how to design the wideband with using the single feed. So this is the typical microstrip, circular polarized microstrip antenna structures. So you have the ground plane, you have the radiator. So the main thing is the radiator, how you are designing the radiator for circular polarization. So you need asymmetry to generate the two resonant mode with 90 degree phase difference. So if you have the slightly difference in the nearly square patch, L very close to the W, so you can generate the two mode, one here, one, but you are feeding in the diagonal direction. In this case, you cannot feed in the orthogonal direction. You cannot generate the two mode. So if you have the nearly square patch, you have to feed in the diagonal direction. So if you are truncating the corner of the square patch equal length and width, and truncating the corner and feeding in orthogonal direction, you can generate the circular polarization. Same if you are adding the stub in the diagonal direction, feeding in the orthogonal direction, you can generate the. So this asymmetry should be either this footing, this the angle. should be in the this diagonal angle. If you are feeding in the orthogonal direction, the asymmetry in the diagonal direction. Same in this. This is the asymmetry in the diagonal direction. So this is the way you can design the single feed. But again, this type of antenna is the narrow band. So you can see the if you have the two more, like one is there, one is there. So in between you can get the good circular polarization. So I will show you how to get the good axial ratio between two modes. So I have done the experimentally. So if you have the truncated corner or nearly square patch or the same bandwidth is almost same all type of this type of the antenna. So if you have the two mode like this, you can have the one here, and in between you can get the minimum axial ratio. So circular polarized frequency of the antenna defined by using the combination of the two mode divided by two. So that if you have the mode 1, mode 2, orthogonal and vertical mode, the vertical and horizontal mode, and then divided by 2, you can get the pure circular polarized frequency. The minimum axial ratio, we call the best circular polarization. The bandwidth of the circular polarized antenna defined based on the 3 dB axial ratio. So bandwidth is defined based on the 3 dB axial ratio, and this antenna bandwidth is this one. But this bandwidth should be within the 10 dB return loss bandwidth. Otherwise, antenna not work well. So for circular polarized antenna, axial ratio bandwidth is important, but this bandwidth should be within the 10 dB return loss bandwidth for proper antenna function. Otherwise, they are not efficient. If your bandwidth in the not in within the 10 dB return loss bandwidth, so antenna cannot work very well. So the gain is very low. So based on this concept, we have designed the compact antenna using the slit method. The slotted method is the one advantage. You can reduce the size, electrical size of the antenna, and generate the two modes. So using the cross slot in one of the diagonal direction and feeding orthogonal direction, we can reduce the size of the antenna and generate the circular polarization. So you have to think how you are creating the asymmetry in the patch radiator, square patch radiator. So different way we have created the asymmetry. Some of my students thinks very smartly, so they have designed very interesting design like TOR shape, like F shape, E shape, C shape, like different shape. And we have published in the some of the top journal in the antenna propagation, and I think this is the base of our most of the antenna. So first antenna this we have developed. So based on a smaller slot in the one of the corner, larger. So based on this, we can generate the circular polarization and designing the very compact radiator size. So electrically small and designing the circular polarization. This is the advantage. So this paper citations, I think more than 300. And other techniques, we use the slit, using the slit in different diagonal direction with slightly different length of width. You can generate the circular polarization. So this also paper is very highly cited. So we have created the different way of the asymmetry using the slit. This slit also can reduce the overall size of the antenna and designing create the two mode with 90-degree phase difference for circular polarization. And we have created in different way of this one is smaller, this is larger. And one of the student have designed this very smartly, continuously changing the width of this one, smaller, larger, like this. Another method we have used designing based on the stub loading. So we have loaded the stub in the diagonal direction in different way, like circular, very small circles, and micro stub. and different patch, different slotted patch, and we created the design the circular polarized antenna in different ways. And using the for designing the wideband using the single feed, so we have used this stack technology. So we have developed, I think, very long back, 2007, and this stack technology can get the wider bandwidth, but the problem is the size. So we have reduced the size using our technology, like slit and slot technology, combining with this, like radiator is slotted and parasitic also slotted. So we can design the overall compact size with wider bandwidth, single feed with wide circular polarization. So using the stack technology and compact design using our slit and slot combination, you can design the wideband circular polarized antenna. And there are some monopole type antenna, you can design wider band. And we have also designed the wideband metasurface based circular polarized antenna using single feed. So if you have a metasurface grounded, we call the artificial ground or metasurface ground or partially reflect metasurface ground or something. So we put the top of this patch and we can have the wider bandwidth around to 30%, 28, 30% bandwidth. Either stacking or using the single patch with single feed, we can design a wider bandwidth. And this is the stack patch antenna, and some of the students have designed the dual circular or dual metasurface based wider circular polarized antenna. Recently, one of the students designed this type butterfly type metasurface unit cell for wider bandwidth. And we have also used the metasurface with DR over the metasurface for wide band circular polarized antenna design. So we put the DR top of the metasurface with single DR. We can design the wider band. We can get the wider bandwidth. And based on this technology, slit and slotted, we can reduce the size of the antenna and with wider bandwidth and high gain. So in this patent, US patent, we have this is the main patch. We have the ring slit and slotted to with grounded to reduce the size, because this can have some capacitance, create a capacitance inductance to overall. We call also this the mushroom type of structure, single mushroom type. So this can reduce the size, and the other is can generate the two mode. So we use this techniques to reduce the size and generate the two mode for circular polarization, 90-degree phase difference. And the parasitic patch further enhance the bandwidth and the gain of the antenna. So we granted this US patent based on this novelty. And other US patent, we have this technology by combining this the slit and the slot technology again, and the feeding network we use some smart way. So this lower band for 900 band, we use this the patch 900, and then we have the one hole to come up this exciting this patch. So this patch also, or this feeding also have the novelty. So this ground plane or this patch is the ground plane for this radiator. So we can generate the two band 900 GSM band and the 2.4 Wi-Fi band. So this antenna can harvest the energy from the 900 band and the Wi-Fi band. So this one, this patent for energy harvesting for dual band antenna, and the main advantage of this antenna have the very high gain in both bands. I will discuss in later on the detail. So this is the one band. We use this slit patch radiator. You can see the slit width inside is different in the different direction. So based on this, we can reduce the size and generate the two mode if you're feeding the auxiliary. So we use the proximity feed to excite this antenna, and this is the feed, microstrip feed to excite this patch antenna. These are some dimensions you can see. And here you can see the comparison. If you have the antenna without any slit, so the frequency is around 1.04, and if you create the slit, the frequency can reduce. So you can reduce the frequency from 104 to 900. So you can design the electrical same aperture, same ground plane. You can design the electrically small antenna with circular polarization using this slit antenna. So there are the two advantages: side direction and the generation of the circular polarization. So student, I think very smartly generated some equation how can design these slit with different direction. Here are some equations. You can see this paper. This is a very long paper to have the. So this is the just electric field distribution, different directions like 0, 45, 90, 180. So the electric field moving with the phase changes. This is the surface current distribution. You can see the most of the current surface current is on in the slit. And one of the advantage of this type of the structure, we can get the very wide beam, almost cover the minus 90 to plus 90 within 3 dB range. So this antenna can receive the energy from whole hemisphere like this. So can receive the energy from all directions from the top of the hemisphere. So we have fabricated in-house, you can see, and then you can see the very good agreement between the measurement and the simulations. You can see the here 900, and you can see the axial ratio. Axial ratio is very sensitive parameter of the antenna, so we can get the very within the 3 dB range axial ratio, and gain is the more than 5 dB. And you can see the major pattern. You can see some repeal in the major pattern. You know, the circular polarized antenna measurement is the spatial measurement. If you design the correctly, if you want to measure the correctly the measurement of circular polarized antenna, you have to the some special arrangement. The measurement of the circular polarization, we use the transmitting linear polarized antenna. So the polarization of the transmitting wave is always changing. So we put our antenna here, antenna under test. So this one moving the azimuth. So you can see if this is the very smooth, it means the perfect circular polarization. If you have some ripples, it means you have the axial ratio. But these ripples should be within the 3 dB. So you can see the minus 90 to plus 90, half hemisphere, almost within the 3 dB. So beam width of this antenna is very good, can cover the minus 90 to plus 90 and receive the energy from all directions. If this antenna is linear polarized, the ripple will be like this, more ripple. So this is the best method to characterize the circular polarized antenna, because this transmitting linear polarized horn antenna rotating, it means the changing the polarization continuously, and this is the receiving antenna. So if you have the perfect circular polarized antenna, you can receive very smooth way. So this is very good antenna which can get the almost within 3 dB axial ratio. And then we have designed the composite right left hand based rectifier circuit, matching circuit for this antenna at 900 megahertz. So we use the voltage doubler topology for rectification, and this is the matching circuit. You can see the composite right left hand based mathematical based matching circuit. Using this composite circuit, right and left-handed transmission line, we can reduce the size of the matching circuit, and overall we can reduce the size. Or these are some parameter of the designing the voltage develop, impedance of the voltage develop. and the right-handed part of the composite right left-handed transmission line. And then we have connected the just connected by using the connector this rectifier circuit, and we have measured. You can see the comparison of the measurement and simulation is not good because we have not optimized the matching circuit. So if you have the perfect matching circuit, which can transfer the receive power to the rectifier, you can get the very good agreement. So here we have not optimized the matching circuit. And then I will discuss the dual band efficient circular polarized rectina for RF energy harvesting. So main motivation of this work is to how to get the high gain in both band, GSM 900 and Wi-Fi band. So we use the same structure like for 900 GSM band, slitted patch antenna here. And for the Wi-Fi band, we use this circular patch with the circular slotted, smaller and larger. We can create the two mode for circular polarization. So we put the top of this for Wi-Fi band, and this is the feeding line and connecting the feeding with from this patch radiator. So this radiator GSM band is the ground plane of this Wi-Fi band antenna. So we use this topology, and this is the feeding and connecting via here. And these are some equations how we created the slit and the distances from the slit. And this is the top patch. And you can see again the reduction of the size using the slit and the slot. If you're creating the slit, you can reduce the frequency from 1.05 to around the 900 megahertz. So you can have the electrically small patch at the same area of the ground plane. And other one you can see also if you have the slot in the circular patch, you can also reduce the size and you can create the two mode, and you have the axial ratio at within this. So this is the technology how can generate the circular polarization using the different type of the slot and different type of the patches. And this is just the field distribution, electric field distribution, different phase 0, 9, 45, 90, 135. This is the GSM band for silted pad, and this is the top patch for Wi-Fi band. You can see the electric field is changing with changing the phase of it means the circular polarization. And this is just current distribution on the 900 band, GSM band. You can see the most of the current near the slit of the radiator, and this is the at 2.4. You can see the most of the current on the top of the patch, and this is the very sensitive. The slotted is the sensitive part. You can see this is the emissions of the antenna, how the wave moving circularly. And we have fabricated. You can see the measurement and the simulated result. Very good agreement between the return loss simulated and measured. You can see, and this is the gain. And gain is the more than 5 dB in both band. And this is the axial ratio. The axial ratio also you can see the less than 3 dB at the 900 and 2.4 gigahertz. These are some measurement performance of this antenna. So main focus. Our focus is how to get the gain is around more than 5 dB with the both band. And again, we have measured antenna with the same measurement setup, and you can see at the GSM band 900 band have the very wide beam width. You can see here in both 911 and 910. But in the 2.4 gigahertz, you can see the ripple is very large in some angle. It means in this direction the polarization is circular polarization not good. So within 45 plus minus 45 degree, the axial ratio within 3 dB. So we can see the this because the for Wi-Fi band we need the receive the energy from the top side. So for Wi-Fi we need only the plus minus around 45 degree. You can see the plus minus 45 have the very good within the 3 dB acceleration. You can see. Then we have compared the our design with the some available in the literature. So in the literature, I think they have the some dual feed based. Our antenna is the single feed, so we have the one only rectifier. So the other problem, the dual feed also cannot achieve the gain, similar gain or the more than 5 dB gain in the both bands. So our target is the gain it should be more than 5 dB. So this is also our antenna is very efficient compared to the other. Then again we have designed the uh, dual band rectifier for this antenna structures. You can see this is a voltage doubler circuit configuration for rectifications. We have used a diode, this SC7, and this is the transmission line for matching circuit. We again use this composite right-left-handed transmission line for impedance matching. These are the some dimensions for 900 and 2.4 gigahertz impedance, and we can see that this matching circuit, the rectifier can have the 900 and 2.4. And we have fabricated and combined with the antenna. So the dual band antenna, fabricated antenna, and again some difference between the both band in 900 and the 2.4. Measurement and simulation, a big difference due to the matching circuit, and we have used this is the student work in-house fabrication, everything in-house. So we don't have the professional. So we have not got the very good agreement between the measurement and simulations. And now I will discuss about the one of the work, our work on the meta-surface based circular polarized antenna for energy harvesting. This is also two student work, combined work. So one student focus on the power management or this circuit designing, and other student on focus on the metamaterial antenna design. So metamaterial unit cell, they use the J cross shape. You can see this one, and then have to study this phase diagram, reflection phase diagram. So we have designed around 90, around this phase diagram 135 is good for designing the efficient antenna. So this is the substrate for the meta surface. You can see that this meta surface, and this is the top side. We use the slotted and the truncated corner patch antenna to reduce the size. So we use this DC to DC converter, BQ2554, and Dixon charge pump we use for rectifications. So overall, we combined two student work, and we publish in the IMS. And you can see the antenna performance is very good at the 2.45 gigahertz, 2.4. And you can see again the pattern is very good, plus minus 90, almost within 3 dB. These ripple within the 3 dB. It means this antenna also can receive the energy from hemisphere, half hemisphere, from minus 90 to plus 90. And you can see the gain is close to the around 5, and acceleration, so I think very good, close to 0. So this is very good circular polarized antenna. You can see the almost smooth curve. Smooth means 0 acceleration, but we consider the up to 3 dB. So this antenna is very good circular polarized antenna. And This is some experiment we have done for power management system, and the efficiency we can have the around 28%. This is the different power levels. Power input is 1 milliwatt and 100 microwatt. The depend on the efficiency depend on the power level also, input power level. If you have the high power, you have the higher efficiency. Lower power is lower efficiency. So this is the just to some measurement efficiency. If you have the overall structure, the efficiency is very low at 100 microwatt input power, around 15.2, and at 1 milliwatt, we can get around 28.9. So the overall system have some power efficiency because the load and other things. This is the efficiency between different input power. So this is also, I think, one of the very good work from the student. And now I will discuss a little bit about some interesting design of our student. They use the like TAW shape symbol to design the antenna, circular polarized antenna, and the E shape symbol. You can see this is the structure, typical structure. So in circular patch, we have created the E shape in one of the orthogonal direction, and the feed in the diagonal direction. So for circular polarization to create the two mode, one here, one here. So one mode have the slight difference frequency. You can see the electric field distribution 0, 45, 90, and 180 moving circularly. So first student have studied the different shape of the E shape, like a circle and circle with this line and then cut the line. So he come up like this shape. First is the circle like that, and then circle ring and like that. So he has compared. You can see if we have the proposed design, this E-shape design have the larger, without any slot. So if you have the E-shape slot, you have the larger decrease in the frequency, reduce the frequency. It means you are reducing the electrical size of the antenna. So we selected this E-shape, have the more reduction and have the very good circular polarization. Without other slot also can get the TP, but the frequency reduction is lesser compared to the E-shape. The E-shape have the extra current distribution compared to the other shape, this shape. The gain also, I think, close to the 5 dB. So then students have studied changing the diameter of the patch. The frequency, of course, changing, but also can keep the excess ratio within the 3 dB. This is the important thing. And then students have studied changing the E-shape slot position from the center. Any impact, there's a slightly impact on the frequency of the excess ratio, slightly change with changing this. So if you have the closer to the this center of the patch, the more reduction in the frequency based on the excess ratio. So if you have the 3 mm distance, so you have the reduction in the frequency. And then student also study the changing the size of the E-shape. Changing the size, the frequency is changing, but the excess ratio is not good. So if you are changing the size, so the slot size depend on the overall the patch size. So you have to change the circular patch anterior size also. And also study if you rotate this E-shape, what is the impact of the rotation of this E-shape? So there's some impact If you rotate the like 0, 90, 180, 270, so now this shape is the 0 degree, and if you change the 90 degrees, the performance is the difference. So this rotation also have some impact, but the good excess ratio at 2.4, we achieve the 0 degree. But if you have this 90 degree, change the 90 degrees this side, this E shape in the top side, so the frequency reduce, but the acceleration is not good. Then we have fabricated. You can see the very good agreement between the measurement and simulation. Again, you can see the patterns very nice. Some frequency, but other frequency not good, but it's still within the 3 dB. This ratio within 3 dB. And we fabricated and measured. And for student demo, we use this professional rectifier to connect the antenna to check if the rectification is okay or not. We transfer the power wirelessly. We use the same antenna, transmitting and receiving. This is a transmitting antenna. This is the rectification, and then you can see the multimeter 1 volt of 10.2. So it's just for the student demo to understand the concept of this rectifications. And same student designed a different way. He used the TOW shape, patch radiator, and feeding by the aperture couple to get the wider bandwidth. And this is just field distribution from 0, 90 or to 45, 90, changing with the phase. It means circular polarization, showing the circularly polarized, rotating the wave. Again, student did some parametric study with different shape and this. So to optimize the antenna, this is the radius of the TOW shape, and this is the feeding line. Feeding line no impact, any impact of this system. Only the matching is changing because this excel ratio depend on the radiator. And this is also the rotation of this TOW shape. If you rotate the TOW shape, how the performance of the changing the antenna. This is also very good to study. So around 15 or 30, within 30, you can get the very good excel ratio and then matching. And we have fabricated this antenna again, and then you can see the fabricated structure. You can see very good agreement between the fabricated and the simulation, and gain is very high, more than 6 dB, and the bandwidth is very large also, can cover very large bandwidth. This is again we use this rotating method, and you can see at the both side is the ripple is within 3 dB, but this is not good in the plus minus 90 because this is a more directional high gain. So the beam width is the plus minus 45 degrees. So enough for Wi-Fi, receiving the Wi-Fi signal. Again, we student done some experiment to check the rectification. We connected the rectifier and using the multimeter to demo for his project, final year project. Then one of the other students have done this study for master student. Using this we call the stub integrated microscope antenna. We call the SIM, circular polarized antenna, for wide coverage. So integrating this stub in the diagonal direction, feeding orthogonal direction, you can generate the circular polarization. So there's the different cases. The asymmetric stub length case, asymmetric stub gap also have a length. If you have the asymmetric length like smaller, larger, you can generate the circular polarization. Or you have the gap with the stub is the symmetric, and you have the different gap, you can also generate. So there you can make a lot of combinations. So this is the art of designing the circular polarized antenna. So you can make the symmetric stub or symmetric length. You have the asymmetric gap. Like that, different combination you can make. But concept design is same. So how to generate the two mode, create the asymmetry in this direction. So either gap, either this length or this width also have. So there you can make the lot of combination. The student study only the four cases. So the effective length of this patch, we have also studied how we can get the effective length of the this patch to design the resonance frequency, get the exact. So we calculated based on the this formula. We have generated this formula. 1/8 like this connecting this the gap and the width of the stuff and the actual length of the patch, central patch. So based on this, we can get the frequency using the effective length of this. So epsilon effective, we can calculate standard formula. The resonance frequency of this type of antenna, we can including this formula too here. So we can get, these are the some dimension of the four cases, different cases. So this is the asymmetric case. So in this case, the length is the asymmetric, slightly asymmetric. So we can generate the circular polarization. You can see the 0, 45, 90. And this is the asymmetric stub gap. So you can see the gap is asymmetric, smaller, larger, larger, larger. So you can generate the circular polarization. And this is the asymmetric in this direction. The two direction is same and this direction is different. So you can also generate like this. It is the different combinations. This is the length, the symmetric gap and length is changing or width or change. So there are so many combinations you can make. So we have study and we have we have fabricated all four antenna and we have measured. You can see the performance of the major antennas, all major antenna. And the gain is around more than 4 dB, around close to 5 dB. And almost all antenna have the similar performance, only slightly the frequency is shifting. These are again measure the radiation pattern to characterize the circular polarization. You can see the very good XL ratio in the all half a plus minus 90 degree, about the half. And then again, the student done some experiment to transmitting the EM wave to receiving the, this is the antenna user receiver. You can see that some power. So next I will be go through very fast with others. How to design the smart home. If you have the smart home, have the sensor in the different location. So we need a transmitting antenna energy, the multi-beam antenna, or we have the beam forming antenna, or we have the some kind of the changing the beam to charge up the sensor in different location. If we have the energy harvesting based sensors, okay, for smart home design or surveillance. So there are the some software defined programmable metasurface lens antenna, which can generate the beam in different direction by using the controlling this FPG or some programming. So this is also very interesting work. Software defined radio can be used for the beam changing the beam. So in our student done some verify this concept using the butter matrix. You know the butter matrix. If you have the 4x4 butter matrix, you can connect the 4 antenna, which can generate a beam in the 4 different directions to charge up the sensor in different location in the smart house. So for the butter matrix, you should design first the miniaturize the coupler. Coupler means you have to have 90-degree phase difference with the 3 dB in both line, both output. So first design the coupler and we fabricate it and test it. You can see the 90-degree phase difference, 2.4 gigahertz and around 3.5 degree power levels. So 0.5 is the loss in the circuit or in the material or some design. And then we have to have the miniaturized crossover. Crossover means we can cross the power without any phase delay. And no, should we have the same power? Only the some losses in the this structures. Only the I think minus 0 or 0.5 is the loss in the crossover. And then we have designed the butter two 4x4 butter matrix. So the 4x4 butter matrix need the four coupler and one crossover. So total loss of the this 4x4 butter 4x4 butter is around 2 dB. So the power level is minus 8 dB, should be 6 dB. So you can see the different, that is the return loss of the different port S11, S22, S66, and this is the power level, different port. So based on this, the different port have the different phase and can generate the beam in different direction based on the input. So for this one, we have designed the E-shape I have discussed. This is one no need to discuss again. And then we need to connect the four antenna, which are very close each other. Interspacing distance is D, which define the angle of the beam. So we connected with the this butter matrix with the four antenna. You can see these are four antenna with the butter matrix with the input. If you connecting the just RF switch, you can change the beam in different direction with very low cost. So we have the beam in different direction. You can see simulated and measurement, very good agreement, and beam angle can be defined based on this. So the D is the very important distance between the interspacing distance between the two elements. Should be very close. You can get the larger angle. So main beam, you can see the minus 5 degrees, 65 degrees, minus 55 and 20 degrees. So based on the just connect the RF switch, you can switch the beam in different direction. So verification for demo, we have done some experiment in our lab. So this is our transmitter, wireless power transfer 4, using the butter matrix, connected the butter matrix. And then we use the tau shape based our rectifier, which I have presented to antenna, to check the do the this demo. So we have this 1 meter distance between this transmitter and our rectina receiver, the harvester. You can see the here 1 meter distance, and this is the four antenna connected with the. So you can see the maximum voltage we can receive around minus 3 degree, 65 and 53 and 70 degree. So voltage, maximum voltage is 30 milliwatt. And we have also compared with the theoretically very close, very good comparison with the expected and measurement. So this is just a demo for student for the how we can charge up the smart sensor using the very low cost technology. And this is my last slide concluded. So I have discussed the lot of things about the RF energy harvesting and applications, and designing how we can design the efficient RF energy harvester. And I have discussed various combination of the antenna, various of the antenna, and I discussed some of the polarization and circular polarized antenna, dual circular polarized antenna, and how we can use for RF energy harvesting. And also I have discussed some new topic of the like metamaterial based harvester, and then finally I have demoed some how we can use the wireless power transfer and then use the sensor in the different location in the smart house. And I think you have received some of my knowledge, harvesting my knowledge. And the future research area for energy harvesting, I think, man, is the how to improve the efficiency of the RF energy harvesting very low. So how to improve the efficiency and range, and the integration with the IoT devices, also very, very interesting area. How we can integrate this RF energy harvester to the IoT device or wireless network sensors or this small sensors. And this advanced meta surface antennas, how we can use in the IoT applications, and hybrid harvesting system is also, I think, the future research area for energy harvesting. So thank you everyone, and then we have the one conference in the New Zealand. I think all are invited to submit the paper. The conference will be in the August and New Zealand, August 3 to 8 or 7. And thank you, everyone. I think if you have any questions, I think I am very happy to have some questions.
Yeah, so thank you, Dr. Nasimuddin, for your valuable presentation. So now I will ask participants to raise any questions if you have. Participants are requested to raise any questions if you have. Mr. Akhil TV, I think that, and Mr. Prabhu has raised their hands.
I think
So,
you can unmute and then ask directly.
yeah, sir, you can ask any questions.
Yeah.
Hello, sir.
Hello. Yeah.
Uh, Good evening, sir.
Good evening.
Sir, how this metamaterial is helping for energy harvesting? And
Okay.
one more thing, sir, and how we are climbing the antenna is metamaterial because when I'm seeing the slide, I could not see that negative mu as well as negative epsilon.
Oh, metamaterial. I think not like the mu or other thing. Metamaterial just defined based on the because usually you cannot put the antenna very close, right? If you have the two antenna, if you put the very close, you cannot get the same power if you put the unit cell with based on the lambda by 10 or very small unit cell close to. So metamaterial not really need like mu negative epsilon or negative mu. I think forget about this one. So meta surface that's the surface of the very small unit cell. So you just need to check the how much the this meta surface can absorb the energy for in case of the energy harvesting. So you can think as about as the observer. If you have the perfect observer, you have the best energy harvester.
Okay, sir. Thank you.
The you cannot use as a antenna meta surface. Use as a observer.
Okay, sir.
Okay, so any other participants, do you have any questions?
Again, unmute and then ask.
Okay, so I think that near there is no other questions, and also
So today is the last day, right?
today is the last day. So, sir, I think that there is no further questions from the participant side.
Okay.
So, sir, thank you once again. Thank you very much for your
Thank you.
nice presentation,
Thank you
and
so
also thank you for your valuable time.
time.
In
Yeah,
the
very
meeting.
good.